Hi guys, it's a pleasure to be here. I always enjoy coming back to GSWA, and so this work is really about a year's worth of work on a bit of an enigmatic dyke. It involves collaboration with a lot of people at Curtin, but also it's involved quite a lot of people at the survey as well. By the way, if anyone has seen this movie, I'd be quite interested to hear about it because it seems to be set in the Western Isles, but I haven't managed to get a copy of it. Okay, so what's our toolkit to really understand the deep architecture of cratons? Well, you know, we can, I guess, drill, but that doesn't get very deep. We can use geophysics, as we've heard about. That's a very powerful technique. And we've also heard quite a bit about using, you know, isotope geology to really understand the deep architecture of crust. And this is kind of important because we have a time resolution with isotope geology that enables us to understand how things have evolved through time. You know, so we can have these, for example, hafnium isotope maps that highlights areas of juvenile input, which can be important for understanding crustal domains and large crustal boundaries between domains, which might be where fluids are focused, and obviously that can be important for mineralization. If we look at the maps that we've got up here, we've got a hafnium isotope map on the top left, a whole rock map using neodymium on the right-hand side, and also a map here using lead isotopes in feldspars. Now, these are telling us about different levels of the crustal column. Typically, these maps would be interpreted as telling us something about a mantle, fractionation, extraction of crust in the deep part of the crustal column, whereas the lead isotope map is maybe telling us about somewhere higher up in the crustal column. We can see similarities between these patterns and, you know, S-wave velocities. So it's telling us something about the physical properties as well as the chemical properties of the crust. What I'd also say we can use to image our deep crust is intrusives. And this has been used before with kimberlites, and what kimberlites have brought up within them has been used to kind of probe the deep crust. I'd suggest we can probably also use a range of other intrusives to do this, and that's what the rest of the talk is basically going to focus on. So we're going to go off to the southwest terrain, and we're going to look at an enigmatic dyke just about here. So as we've heard, the southwest terrain appears to have, for the Yilgarn, relatively young granites, about 2.7 to 2.6 GA, although there is some older components that we've heard about. And the siliciclastic sequences that these granites intrude into is not very well known. We've just got maximum depositional ages. So we're going to go close to the major structure here, the Darling Fault. This is one of the biggest fault systems in Australia. And we're going to go to an unusual intermediate composition dyke. Now, if you're a geochronologist or an isotope geologist, these are probably about the worst type of rocks to try and do work on. They're not happy in their current chemical environment. They're strongly altered and they're changed to amphibolites. They typically don't crystallize much zircon, so they're pretty hard rocks to work on, but I think they can still be quite interesting and informative. So the dikes themselves form this discontinuous north-northeast trending package. They're foliated and they're quite leucocratic, and there is a late-stage vein system that cuts the foliation. So they've seen a prolonged geological history. So we took a fist-size sample, and all the data you're going to see for the next 20 minutes basically has come from a single fist-size sample. So I just want to show you how much information we can get from that. Let's start off, get Hugh involved, get Hugh to look at some of the whole rock geochemistry. So the whole rock geochemistry is quite interesting. So we see here on a rare earth chondrite normalized diagram. The dyke labeled SW1 is the dyke we're talking about. You can see it's relatively evolved. Composition is quite clear, and I'd point out it's very similar to this Bibikine dyke suite that's recently been reported by Camilla Stark in 2018. You can see it's quite different from Morbs, and it's heading on its way up to something a bit more enriched. In terms of its silica content, it's about 54%, so it's still, you know, quite intermediate, quite difficult to work with. And if we look on the right-hand side here, we've got some petrographic images. We can see it's most of the primary mineralogy has been converted to amphibole. So what do we know already about this Bibberkine dyke suite? It's known from close to Pingelly, just east of Perth. Suite of dykes you can see highlighted in blue, and they're pretty challenging to work with. So some badleite grains have already been worked on by shrimp. You can see the shrimp data is scattered. It's not fantastic, and that's part of a reflection of the overprinting history these rocks have seen. Nonetheless, Camilla was able to do a great job by getting some crystals and doing Tim's work on them, and we get an age of about 1319 MA, which was interpreted as the magmatic crystallization age of primary badleite, so that was interpreted as the primary crystallization age of these Bibberkine dykes. In terms of what's happening elsewhere at that time, that's roughly the same time as the Lungana arc is forming somewhere outboard the AFO. Whether it's connected to the Moss and Curtin or not, we don't know, but that's somewhere in this oceanic realm east of the Albany-Fraser origin. So at that time, we're getting dykes being emplaced within the southwest terrain. Okay, so here's analysis from a single chunk of rock on a single thin section. The different colors reflect analyses of pretty much every uranium phase we could find. So we have in red zircon inclusions in titanite, in yellow matrix zircon, in green a lot of titanite analyses, and in blue apatite analyses. Now I'm showing these diagrams slightly differently to the diagrams that Tony showed. I'm using inverse Concordia space, but what you want to take away from this diagram is data is concordant when it falls on the blue line. But you can see we mainly see these trends that are mixing lines between a common lead component, which is the component that isn't produced from radioactive decay, but can be like a geochemical signal, if you like, for that mineral, but also the radiogenic component, which plots at the bottom end of these arrays. So the array itself contains quite a lot of information. So what's going on? Why are we getting this wide array of different ages? Well, these minerals have different responses both to temperature but also to fluids. They have different reactivities to fluids. For example, zircon might be more robust than titanite to certain fluids, but apatite, has a very low closure temperature, is telling us about later events in the rock. So by piecing this information together, we can get a rather complete history of the geology of this region simply from a single sample. Okay, so in a mafic to intermediate magma, zircon is not going to be very happy. You can see here some modeling work that's been done, and it suggests at 1,000 degrees C in a more primary magma, you're going to kill your zircon pretty fast. It dissolves. So how are we able to preserve these older grains? Well, it's pretty clear they're inclusions in titanite, so that might be a good way. So we have some shielding effect. If we look at the petrology of the grains themselves, we can see that. We can see the titanite nicely encloses these zircon inclusions. Analyzing zircon inclusions by any technique is not easy. They're small and we only have a transient time signal. So what we're looking at here is time against chemistry. And we can see our laser ablation started off in titanite and then drilled into zircon. Drilling into zircon, we get more uranium and thorium. Greater uranium and thorium gives us more of a radiometric signal, gives us a more concordant data point. So we can see that on these diagrams that compare common lead to zirconium content. So our zircon data is much more concordant than our titanite data. Titanite, when it grows, incorporates lead. That's common lead. That gets in the way of our age interpretation. The point is we can use our chemistry through the time of the laser ablation to try and hone in on where the inclusions are and get a date for them. All right, so some of the zircon inclusions appear particularly old. So we have one inclusion here. If we subset this ablation into different analyses, so at the back end where we're going into the zircon inclusion, at the front end we're mainly in titanite, we can see what that does on a Concordia diagram. So that zircon inclusion is interpreted as 3.4 billion years old. The titanite it's encased in is lying on a common radiogenic mixing array that has an age of about 1.1 GA. So these are inherited crystals that have been incorporated within titanite. That titanite has shielded these grains from later re-equilibration in this dike. We can see a range of other ages within the zircon component, so those are highlighted in red. We have this old component pointing to 3.4 GA inherited age. I highlight that while there's a small number of analyses, we can't explain analyses within this red triangle without having that component. We also have another younger inherited component pointing to a component at around 2 GA, but we have everything down to a component at about 1380 MA, and you remember 1390 MA was the crystallization age of this dike, so it looks like some of this zircon component may be newly grown material within the crystallization timing of the dike itself. Okay, so let's look at our matrix zircon. As I said, our matrix zircon isn't very happy. Tony had lovely pictures of zircon. I've got these horrible things, sorry. So these zircons have clearly reacted in later fluids. You can see there's various alteration zones through them where we're getting this low CL phase growing and eroding these dark grains. These dark grains have actually quite high uranium. They're highly reactive. They've dissolved and regrown. We see a range of ages coming out of these crystals. Can we do something else to try and constrain some primary information out of these matrix zircons? Well, yes. Hafnium is more robust than lead, so it doesn't diffuse out of the crystals as readily in fluids. So if we look at our hafnium isotope system, we can maybe extract some more information. So this is where our data plots when it's measured and plotted against the time of apparent crystallization of those matrix zircon. But that's really a reflection of alteration and lead loss. If we recalculate back at the time of dike emplacement, we have information that seems to make more sense, where the hafnium isotopic system spreads between a chondritic composition and something that's a bit more like depleted mantle. We can definitely say those matrix zircons are not an Archean component that's been incorporated into the dike. They reflect a newly grown component, because if we calculate the hafnium at an Archean time, you can see they would not be plausible. They plot with impossible compositions. All right, continuing on this single thin section we're blasting to death, we've got a lot of titanite, and that's highlighted in orange here. So our titanite, again coming back to this diagram, is in green, and you can see it has a spread between ages of as old as 1360, so that's a minimum age for the crystallization of our dike, consistent with our zircon constraint of about 1390, to as young as about 400 MA. On this diagram here, we're plotting the ages. So in green, you can see there seems to be a peak at around 1 GA, and I'll come back to that 1 GA and why it's important. We can use chemistry of those titanites to get further information about the process that's ongoing. So this is a rare earth plot for those dated titanite grains. And we can see in green, we seem to have more depleted chemistry. Green ages are younger. Older ages with more yellow seem to be less depleted chemistry. So what's going on is basically there's a fluid rock interaction event that's altering the rock, but it's also altering its mineral cargo, and it's altering the titanite to give us our younger apparent ages. We can see this on a little bit more complex diagrams here, where we're looking at the slope of the rare earth diagram against age. So you can see younger ages are more depleted, older ages are less depleted. The zircon inclusions are even older, and we can see also the influence of allanite inclusions within the data set. All right, getting there. That's just pointing out the oldest titanite component that provides us a kind of constraint on the minimum age of the primary dike. We've also got apatite, so let's have a crack at apatite as well. Apatite's in blue, coming back to the same diagram. You can see it lies on a mixing line with a radiogenic component at 210 MA, so conventionally that would be interpreted as the time to pass through about between, say, 400 and 600 degrees C. We also have information about the common lead composition as well, because a lot of the titanite analyses don't have any uranium. They're primarily just lead. this number for the common lead component is actually quite useful. So we can compare that to regional lead models constructed using feldspar, and we can see that for this composition, it kind of corresponds to what we would expect as a crustal lead signature at about 1100 MA. So everything is seen to tying together now. We basically have titanite that's recrystallizing and apatite that's potentially growing at 1100 MA. That apatite itself is going through a later cooling history. The 210 age for the apatite is actually quite important. So if we look at that in terms of the stratigraphy of the Perth Basin, it's when the Collie Basin was forming. We have rifting happening within the region at that time, and there is also volcanics known at that time, so there maybe is a heating event at that time. It's kind of useful to have that time constraint because the palynology is quite difficult through this section of the basin. The 210 age also corresponds to other isotopic evidence of peak denudation within the region when we're getting uplift and the formation of extensional space as well, roughly at the same time. All right, let's try and piece this back together into a space-time diagram as we've seen before. So we've got inherited components here that seem to have a similar age to the Dougal gneiss, for example, in the Narrier. We have information about the dyke being emplaced, which seems to be at around 1400, 1390 is about the best guess. We have a whole wide range of ages, mainly indicated by titanite, that reflect the Pinjarra orogeny, with a clear age indicated at about 1 GA when most of the materials seems to have been recrystallized. We see additional fluid rock interaction events all the way down to, actually, I should point all the way down to the Lewin, so we see events associated with that as well. And then our apatite is recording this very late event, all within a single thin section. So what do we think happens? Well, we basically think our Bibikine dikes have transited through the crust and picked up some Paleoarchean inheritance. In the region, there is some very rare other evidence of Paleoarchean components, mainly coming from xenocrysts and also detrital zircons. So we would say that in the southwest, there is a very old basin component. Now, whether that that inherited component is coming from an ancient sediment or an ancient magmatic rock, we don't know. We also have other evidence of an ancient basement in the southwest terrain coming from modern river sediments. So literally, if we go straight out the door there and down to the Swan River, we're going to find Paleoarchean to even Eoarchean components. So we've done a recent survey looking at the river all the way out to Rottnest. And if I just summarize that with this blue diagram, you can see we can find really ancient components within the detritus of the river itself. If we look at, so these are probability age spectra, the 3.4 inheritance in the dyke is indicated in the yellow bar. What I want to highlight is that that age is actually quite a common component in the inherited component within granites, but also within metasediments from other units within the Yilgarn, like the U and Me terrain, but also we see it within the southwest terrain as well. The question then becomes, how do we get this ancient basement component? Two ways. I think one is definitely preferred. One is we have a piece of, I'll come back to these, a piece of the Narrier that's been moved along the Darling faults. The other is that there's actually a true deep basement sitting underneath the southwest terrain, stretching all the way up and wrapping into the Narrier. On the left-hand side, we've seen these hafnium diagrams before, so this is just a compilation of all the data we have for magmatic rocks at the top from sediments, including modern sediments on the left. The two diagrams match, and we can see really how crust responds. It gets reworked. We have periods of new juvenile addition when the data stair-step upwards, and we continue this pattern. What I want to point out is the old evolved array in this material heads back to about 3.8, and that is a planetary-wide signature. That's about as old as we can get. There's two exceptions to that, one in Casta and the other is Jack Hills, but they sit on different styles of array. But this 3.8 array seems to be picked up in the deep basement of much of the western side of the Yilgarn. And I would suggest that the Yilgarn is simply built out of this deep crustal nuclei eastwards. In terms of the boundary of the southwest terrain, it's quite well defined with Mercury anomaly. If I can get back to it, yeah, we go. Mercury anomaly in regolith, but also in modern seismic data, which was the other indication. So we seem to have this sliver, which paradoxically has young granites, but it seems to have a much older basement history, and part of that history is trapped within this dyke. So I'll leave it there. Thanks very much for listening to me.